We'll start this video by proving a neat application of the finite field material we've developed so far. So this is corollary 16 in section 14.3. It says the irreducible polynomial x to the fourth plus 1 in z bracket x is reducible mod p for every prime p. Okay, so first, this polynomial, remember this is kind of a nice example. We showed that this is irreducible by applying Eisenstein's criterion, thinking of this polynomial not as a polynomial in x, but as a polynomial in x plus 1. Okay, so why is this result interesting or important? If you have a polynomial in z bracket x, it's tricky sometimes to tell whether or not it's reducible. So it's easier to factor a polynomial in fp bracket x than it is to factor it in z bracket x. If you have a polynomial that's reducible in z bracket x, when you factor it mod p, you'll get something that is reducible because you have these two factors and each one reduces mod p. So if you take your polynomial and you factor at mod p and you get something irreducible, then you know that your original polynomial was irreducible, because if it was reducible in z bracket x, then it would be reducible mod p as well. So one question is, you could say, well, I have some polynomial in z bracket x. I'm just going to factor it mod p. And if I never see anything irreducible, then I'm never going to be able to deduce that my original polynomial was irreducible. So if I factor mod p and I get something reducible every single time, am I allowed to conclude that my original polynomial was reducible in z bracket x? Like, you just keep factoring mod p and you always get something reducible. Does that mean that your polynomial was actually reducible? And this example shows that the answer is no, that there are polynomials that are irreducible in z bracket x, but you reduce mod p and you get something reducible for every prime p. Okay, so this corollary is showing that one nice way that you might want to determine whether or not a polynomial in z bracket x is irreducible or reducible just doesn't work. All right, so let's prove this. Like many things in algebra, p equals 2 is a special case here. So what happens when you factor this polynomial in f2 bracket x? So you reduce the coefficients mod 2, and you get, okay, x to the fourth plus 1. Well, that is x squared squared plus 1 squared. And a to the p plus b to the p is a plus b to the p. So that is x squared plus 1 squared. But now we just do the same thing on the inside. This is x squared plus 1 squared squared, and x squared plus 1 squared is x plus 1 squared. So this is x plus 1 squared squared. So it's x plus 1 to the fourth in f2 bracket x. You don't have to do it this way, but the point is it's reducible mod 2. You could see that more easily just by seeing that it has a root at 1. Okay, so for the rest of the argument, we just have to show that for every odd prime, this polynomial is reducible. And there's a clever idea here. What we're going to do is consider x to the p squared minus x. Remember, the finite field of order p squared is the splitting field for this polynomial over fp. This factors. This is x times x to the p squared minus 1 minus 1. There's a factor of x, clearly. And the clever part is to think about this p squared minus 1, where p is an odd prime. P is an odd prime. I mean, if p is an odd number even, p is equivalent to 1, 3, 5, or 7 mod 8. So what happens when you square it is you get 1 mod 8. There's always one more than a multiple of 8. So that means 8 divides p squared minus 1, which is this exponent up here. Why does that matter for factoring polynomials? Well, exercise 3 in section 13.5 says that d divides n if and only if x to the d minus 1 divides x to the n minus 1. Okay, and there's a little note on that exercise that should help you to prove this. You should do this exercise if you haven't done it already. If n is qd plus r, so apply the division algorithm and you write n as qd plus r, then you can rewrite x to the n minus 1 as x to the qd plus r minus x to the r plus x to the r minus 1. Okay, so I will leave the details to you, but let's use this result. What does this mean? 8 divides p squared minus 1. So that means x to the 8th minus 1 divides x to the p squared minus 1 minus 1. Okay, so why is that relevant to what we're doing here? Well, we know how x to the 8th minus 1 factors. This is a difference of two squares. This is x to the 4th minus 1 times x to the 4th plus 1. Okay, so what's the point? Is this polynomial that we care about, x to the 4th plus 1, divides x to the 8th minus 1, which divides x to the p squared minus 1, which divides x to the p squared minus x in fp bracket x. So all of the roots of x to the 4th plus 1 are roots of x to the p squared minus x. And what is this collection of roots in a splitting field for this polynomial over fp? That splitting field is fp squared. This set of roots is a finite field of order p squared. It's a degree 2 extension of fp. So what does that mean? If you adjoin all the roots of x to the 4th plus 1 to fp, what extension are you generating? Well, all those roots are contained in a finite field of order p squared. So the extension you get by adjoining all the roots of this polynomial over fp has degree at most 2 over fp. It might actually have degree 1 if this factors completely, splits completely already in fp bracket x. But certainly, you adjoin all of the roots, a splitting field for this polynomial over fp has degree at most 2. And if this polynomial were irreducible, then adjoining one root of this polynomial, well, if this were irreducible, you would join a root, that is, you're adjoining a root of a minimal polynomial, you would get an extension of degree 4. So that's telling us that x to the 4th plus 1 is not irreducible in fp bracket x, because when you adjoin all of the roots, you're not getting an extension of degree 4, you're getting an extension of degree at most 2. Okay, so this idea is very clever the first time you see it, but this is a really nice example to keep in mind that this can happen. So I recommend really thinking about this argument. So I'll pause and erase, and we'll talk about additional things we can prove given our finite field material so far. We'll next prove proposition 17 in section 14.3, which says that fp to the n is a simple extension of fp. That is, there exists an element alpha in fp to the n such that the field generated over fp by alpha is all of fp to the n. Okay, so it's clear that we have inclusion one way, that the field generated over fp by alpha would be contained in fp to the n, because if alpha is in fp to the n, then certainly so is the field fp adjoin alpha. But how do we know that there's one element alpha that gives us the whole field? Okay, so we'll see that once we know this result. In particular, that means that there exists an irreducible polynomial of degree n over fp for each n at least 1. The proof is straightforward. The multiplicative group of fp to the n is a cyclic group. Okay, so take theta to be any generator for this group. We know there's at least one. And we can see that fp to the n is equal to fp adjoin theta. Because, okay, we clearly have inclusion this way. fp adjoin theta is in fp to the n. But just by taking powers of theta, we get all of the elements of fp to the n star, the multiplicative group. That's what it means for theta to be a generator. So we have inclusion the other way too. Okay, so that shows that fp to the n is a simple extension of fp. And now we just need to remember that what is fp adjoin theta? This is isomorphic to the quotient of fp bracket x mod the ideal generated by the minimal polynomial of theta over fp. So if this minimal polynomial is an irreducible polynomial of some degree, but fp adjoin theta has order p to the n, so this field has to have order p to the n as well. So this must be an irreducible polynomial of degree n in fp bracket x. So that completes the proof. I want to point out that more is actually true here. It's not just that there exists one element alpha such that fp adjoin alpha is fp to the n, But the number of primitive elements, the number of elements alpha in fp to the n, such that fp to the n equals fp adjoint alpha, is the number of generators for this cyclic group, fp to the n star. How many generators are there for a cyclic group of order n? Well, that's the Euler phi function, phi of n. So what's the order of this cyclic group? It's p to the n minus 1. So the number of these primitive elements is Euler phi of p to the n minus 1. So, okay, all you need to do is note that if you pick an element that is not a generator of this multiplicative group, if it generates a proper subgroup, then the field that you get generated over fp by that element is not all of fp to the n, but is some proper subfield of fp to the n. And I'll leave the details for you to think about. So I want to point out that this came up on a recent algebra qualifying exam. This is one of the exams from 2019. I can't remember if it's fall or spring. Problem number 7. Okay, so where are we now? So we know that there is at least one irreducible polynomial of degree n in fp bracket x. But how many are there? We know there's at least one, but maybe there's more than one. So that's one question to think about. And then another question is, how do we find one? So we know that there's an irreducible degree 4 polynomial in f2 bracket x. How do you find one? Do you just write down all the monic polynomials of degree 4 in f2 bracket x and then try to factor them? You could do that, but once the degree n and the prime p are big, that could take a very, very long time. So we'll talk about these questions in the next video.